Pistons, Pistons, Pistons. The unsung heroes of your engine. They're like the offensive line in a game with the old pigskin. Go deep, Kanan! They're constantly getting their ass kicked and you never notice unless one breaks down. But these seemingly boring looking hunks of metal are engineering marvels. They get hit with hundreds, thousands of pounds of force multiple times a second for hours on end, and they don't even complain about it. Most of the time. Cast, billet, forged, which is the best? Which one's the strongest? Which one makes all your friends super jelly? We're gonna figure it out. Oh, and also we teamed up with the hydraulic press channel because we're gonna put some of these in the crusher. That's how we do it here on B2B. We bury the B. Let's go. Thanks to Keeps for sponsoring today's video. Oh, hey there. It's Dave's birthday, and we're here celebrating at his favorite restaurant, Cherry Dave's, or what I like to call Cherry Dave's. Ain't that right, Dave? So, Dave, do you like your birthday gazpacho? Well, they don't have cake, Dave. Besides, gazpacho is cold just like cake, so just close your eyes and play pretend. Hey, sometimes in life you can't get what you want. Okay, look at me, Dave. You think I wanted to be one of the 2 out of 3 guys to experience some form of male pattern baldness by the time I was 35? Not a chance. If only I had used Keeps. You see, Keeps makes hair loss prevention easy by giving you access to real doctors online. Plus, they'll ship you your hair loss medication directly to your door every 3 months. So start your hair loss prevention today by going to keeps.com/B2B or click the link in the description to receive 50% off your first order. If I asked you what the main function of a piston is, would you be able to tell me? Yeah, you, Jigen, go for it. Thank you for raising your hand.
It takes small engine booms and turns it into big power booms.
Okay. Not exactly what I was looking for, but good effort. Now, the main function of the piston is to take pressure created during the combustion process and turn it into a force applied to the crankshaft. The piston moves linearly up and down, which turns the crank round and round. Oh, we should make a song. It's pretty good. It's not a one-pony show, though. Pistons have multiple functions. They create the compression that is necessary for combustion to occur in the first place. They seal up the combustion chamber, allowing that pressure to build up, but also they prevent expanding gases from escaping or oil to penetrate into the cylinder itself. They're also a guide, like my spiritual friend, Sri Lanka. Only the piston guides the connecting rod, while Sri Lanka guides me to spiritual awakening. Speaking of that, have you guys seen our new high-low t-shirts? These things are freaking great. It's got a frog on it. I got one for my girlfriend and she kissed me on the lips when I gave it to her. That's what I'm talking about, fellas. Now, using that third eye you now have, you can see why pistons need to be made strong. Now let's use the engine in my Catfish for example. Now if I were to do a compression test on this bone stock LS1, I'd expect anywhere from 140 to 160 PSI, depending on the quality gauge I'm using, as well as the process I use to check it. Regardless, that is cranking pressure, not peak cylinder pressure. Peak cylinder pressure happens near top dead center when the engine is running and under load. Now that is a much harder number to calculate. We could do it, but I'm not gonna. So let's just say it's about 800 PSI. So at wide open throttle, riding at a steady 6,000 RPM, a single piston is getting a power stroke every 2 revolutions. So that's 3,000 power strokes per minute, which is 50 strokes per second. 800 PSI, smack in the face of a piston 50 times a second. Put that into context, the average punch for an adult is around 150 PSI. So just imagine me, a very average guy, but I'm a quintuplet. There's 5 of us, and we're punching you 50 times a second, like this. For like hours and hours and hours and hours and hours. That's what it feels like to be a piston in an LS1. So to take that kind of punishment, they gotta be strong. Like really strong, which is why not only the material type, but how that material is used to form the piston is really important. It's the foundation for its mechanical properties, and those mechanical properties determine how much boom it can handle. So today we're gonna focus on 3 types of pistons: cast, billet, and forged. Starting off with the most common piston type, and that is the cast piston. Now, casting is a process in which you take metal, you heat it up until it transitions into a liquid state, and then you pour that liquid metal into the mold that is the shape of your part. In this case, it'd be a piston. Now, you let that metal cool inside the mold where it solidifies, then you have your part. There are 3 main ways to casting parts. There's sand casting, where the mold is made from sand. There's investment casting, which uses wax plaster mold. And then there's die casting, which uses high pressure to form your part in between 2 metal dies. But the main principle is the same throughout any of those methods. You heat up a metal, you pour it into the mold, you let it cool. We actually melted our own metal here at Donut for an upcoming episode we're doing on casting our very own engine parts. So we finally got our forge. I have all my safety equipment on because it's really hot around here.
What are you making?
Oh, Jerry. Oh, it's not looking pretty good.
Oh, God.
Not looking stable.
Dude, how am I supposed to pour this
Hold on, yeah, I don't think that's right. Can you grab the side of it now that it's out?
Or the side. Yeah, like this side, like the side of the bucket.
Like this?
No, like inside.
Oh, like this?
Yeah.
Nice. T1000, bro. Bro, that was a solid pour.
Wow.
Okay. Exceptional.
Nice.
Thanks for the help, James.
Super clean.
What's an ingot?
That was me making a bunch of ingots out of aluminum cans. What do you guys think we're melting cans for? Leave a comment down below. We still cast a lot of parts today, and there are a few reasons why. Mainly though, it's because it's cheaper. Once you have the mold made, you can essentially duplicate your part much quicker. So if you're needing a large volume of parts, casting is a good way to pump out a lot of identical pieces. But from a design standpoint, there are some benefits too. So you can mix your molten metals to form an alloy. We're going to talk about materials in a bit, but different alloys have different mechanical properties. So if you need a part to be made out of a specific alloy, you can mix your molten metals to achieve the alloy required for your application. You can also cast extremely large parts or parts with complicated shapes. You can actually get more horsepower out of an engine by using cast pistons, because when you cast parts, you can make a more complex shape. So piston designers can go buck wild and shape a piston to alter how the air flows, the fuel distribution, and even how the flame inside the combustion chamber travels. You might have heard of hyper-eutectic pistons before. These are also cast pistons, but they have a higher percentage of silicone in there. Why would you want that? Strength. Hey, but why does that make it stronger? Well, because it makes it stronger. Well, why does it make it stronger? I'm getting there, Chip. Hold on to your material science loving horses. First, we have to look at some even stronger options to cast our hyper-eutectic pistons, starting with how we get billet pistons. Billet pistons like these are made from aluminum billet. Billets, they're semi-finished casting products that come from a foundry. And there are a few ways you can get billets, but a more common method is to directly get them by continuous casting. So you take scraps of metal or raw material or other minerals, depending on what type of alloy you want to make, and you heat them up in an electric arc furnace. Once the furnace surpasses 660 degrees C, that's the melting point of aluminum, you now have a nice piping hot magma. The metal will flow into a mold with the desired shape. So for pistons, that mold is going to be round. And the molten metal is drawn through the mold where heat is extracted by water-cooled jackets around it, cooling the metal until it solidifies. The metal casting moves outside the mold with the help of rollers. They then get cut to more manageable lengths, and then it goes through a series of heat cycles or other rollers depending on the properties the manufacturer wants. From there, you cut those billets to a more manageable size again, and that is where the machining or subtractive manufacturing happens. A highly sophisticated CNC machine removes material using various bits until you reach a finished product like so. But let's say I need something even stronger. I need more beef in a similar package. Where'd I go? Well, I go get my forge on. Man, you could eat off of that. Now the neat thing about forged pistons is that they start off the same as a billet piston, with a chunk of billet aluminum. That billet is heated up in an oven and then placed into a preheated die in a forging press where the temperature is around 400 degrees C. The press, either mechanical or hydraulic, uses anywhere from 1,000 to 2,000 tons of force to press that billet into the shape of the die. It goes through a couple more processing steps and ends up getting machined to produce what I have here. So now you know how each of these 3 types of pistons are made. Why is one stronger than another? Well, to understand that, we need a microscope and a basic understanding of crystals. No, not those crystals, Sri Lanka. Gosh, crystal people are weird. Let's start off by looking at metal that has no crystals, molten metal, or for our purposes, molten aluminum. As the aluminum cools and transitions from liquid to solid, tiny crystals begin to form and grow from a bunch of various locations called nucleation points. And each crystal moves outward in all directions until it meets the surface of a neighboring crystal. A single, fully formed crystal you see here is called a grain, and the lines that the various grains meet up at are called the grain boundary. Now, the structure, size, and orientation of these grains are a result of a few factors. The first is the material composition. Now, in most cases, pistons aren't of a single composition. They have small percentages of other metals, and we call those alloys. If you were to go down to your local metal shop, they will have a bunch of types of aluminum alloys with various 4-digit numbers next to them, like 2024, for example. And the first digit, that lets you know the major alloying element. In that case, since it's a 2, it means it's copper. If it was a 3, that means it'd be manganese. If it's a 5, it'd be magnesium. If you're wondering why I skipped 4, it's because I freaking don't remember what it is. The second number, if it's not a 0, lets you know it's a modification of a specific alloy, and the third and fourth digits are arbitrary, but they identify the specific alloy in the series. Remember how hypereutectic pistons have a larger percentage of silicone? That's what number 4 is. 4 is silicone. I knew I'd get it. Well, that silicone content changes the way the grains form. Same thing if we add copper or any other type of metal to the mix. This goes for impurities as well. Those can negatively affect how the grains take shape. And when the molten metal solidifies, it can interact with other phases and contaminations. When we're talking about casting, that could be air pockets in the mold or loose pieces of material like sand. Now, the second thing that affects grain size and structure is the manufacturing process. The process of casting a part is very different from forging a part, and because of this, the grains are different. Forged, billet, and cast parts all have different grain properties due to the process of the part creation. You can think of each process like types of fences. You've got a chain link fence, a picket fence, and a cinder block fence. Each individual link, board, and cinder block is a grain. How those grains link up depend on the method of building your fence. And not only do the types of grains determine the mechanical properties of the material, but also how those grains interact with each other is extremely important. And what's really neat about these grains is that they can be manipulated like Nolan, depending on how you heat or cool them. And because of this, you can adapt the grain structure to a specific application. A samurai sword has a very different life compared to a butter knife. They might be made out of the exact same material, made the same way, but because one application calls for a lot of fruit slicing and the other a lot of buttering, the grains can be altered to fit each application appropriately. Okay, Jerry, this is great and all, but how does the shape, size, and orientation of grains determine their mechanical properties? We always hear about how strong forged pistons are. Why is that? Well, one of the reasons why this piston is stronger than this piston, even if they started with the same material, is because of grain flow. Now, grain flow is the directional orientation and distribution of metallic grains. And when your goal is strength, you want those grains to be uniform. They should be roughly the same size and shape. And you want the grain boundary to be coherent. So when we're talking about metals, if we say a boundary is coherent, we mean that the atoms on either side of the boundary layer have 1-to-1 matching bonds. And the reason for wanting those types of grains is that when some sort of external force is applied to the part, the grains, they want to slip, passing the force on to the next grain in the same direction. So when you have multiple grains but slip planes at different angles, the force being passed through needs to be much greater in order to cause deformation. Deformation is something like this. But why does the force need to be so much greater when the angles are different? Well, think about trying to push a car. If my slip plane is at this angle and I'm passing a force along to this car, if I wanted to move along its slip plane, which is at this angle, I need a lot of force to do that. Duh! Have you ever tried to push a car forward by its side? No. Obvious reasons. Doy! So, smaller, more uniform, and more numerous grains result in a stronger material. Now that we know that, we can look at the grains in a cast, billet, and forged piston using this microscope. But before we do that, who the hell is this guy? The name's Mr. Frizzle. I'm Miss Frizzle's brother, but from Florida. You ever heard of her? She takes kids to space using her magic school bus. I take sexy adult dudes wherever they want with my magic Camaro. Why don't you put that microscope on down, come on in. I'll take you wherever you want to go. I don't know why, but this sounds like a great idea. All right, Mr. Frizzle, let's go. Our first stop is in the cast piston. Now the casting process produces lots of non-uniform grains as well as being larger and less dense. That creates a weaker material. There's also no flow of the grains and we have some porosity. See right here? That's an air pocket created during the casting process. I got an air pocket coming your way. Oh, okay, cool. I don't know why, but I like this guy. How about we take a trip over to the billet piston? You know, Piston was my nickname in high school. Oh yeah, why is that? I think you know why. You know why. All right, Frizzle, take us out of here. All right, let's hit it. Now, billet pistons start off with that chunk of billet we talked about earlier, and then cuts are made to shape the part. Because of the initial manufacturing process that created that piece of billet, we have nice, tight, uniform grains. But look at the grain flow. During the machining process, that flow was disrupted and cut off. The grain flow is parallel, but because cuts need to be made to make the part, the flow has been severed, and because of this, you have a failure point. So cracks will begin to form along open-ended grains. Cracks, sweet. But if we were to take the same billet material and forge our piston, the grain flow changes significantly. Hey, Mr. Frizzle, ready to get forged? No problem, baby, hold on tight. See here how the grains flow along the shape of the part? Because of the large amount of pressure applied to the billet during the forging process, the grains are forced together in a tight, uniform shape. The flow of the grains is in the perfect alignment relative to the force being applied to the part. Remember when we talked about pushing the car perpendicular to make it go in one direction? Well, that's what we have going on here. Because the force is perpendicular to the grain flow, we have an optimal part. So by forging, you can direct the grain flow around critical parts of the piston, like the pin bosses, the skirt, and the crown. All right, Mr. Frizzle, I think that's it. You ready to get back to reality? No problem, Jeremiah. Let's go. Thanks for the ride, Mr. Frizzle. Not a problem, man. I got a feeling I'm gonna be seeing you a lot more often. Heck yeah, brother. All right, you drive safe. See you later. Well, that's it. Thanks for watching, guys. Wait, what? You came here to see some pistons get crushed? I got you. For that, we teamed up with our buddy Lowry with the Hydraulic Press channel. Lowry, let's get crushed. Ow!
Okay, welcome to the Hydraulic Press channel test facility. We are going to test the billet piston against the forced piston. And I have bad experiences about crushing aluminum things. So we are going to keep everything inside of our safety box. I add the polycarbonate here because I think these are going to explode. And I think we are going to start with the billet one. Okay, it's really strong, holy shit. Okay, it didn't explode, but I think it wasn't very far. It's cracked, so the parts could flew out. Whew, that was intense. Yeah, but as you can see, the main pancake part of the piston is still okay, but I think it was much stronger than I thought. Okay, one more crush. Now we have forced piston on its side, so we can better see how the material cracks. And here we go. Okay, that was pretty hard. And thanks for Donut Media for sending the pistons. It was fun to crush them. Yeah, but that is all for today. Thank you for watching and have a nice day.
Thank you guys so much for watching this episode of B2B. I want to thank JE Pistons. They supplied all the pistons for this episode. Click the link below if you want to find some more information on some super sick billet and forged pistons. I want to thank Lowry over at the Hydraulic Press channel. Lowry actually has 2 channels. One of them is the Hydraulic Press channel, which he just puts things in a press. And there's another one, which is a little bit more complex. He builds more things. It's a second channel he has. It's really cool. Both of them will be in the link in the description below. Follow us on Instagram at Donut Media. Follow me at Jeremiah Burton. And until next week, bye for now.